Today I am going to start Module 3 of Chapter 5. In Module 1 of Chapter 5, we have discussed about the occurrence of a parabolic partial differential equations in many physical problems. Among all physical problems, the heat equation or the diffusion equation comes most frequently. For that reason, in this module, we have considered heat equation or the diffusion equation for our discussion. Moreover, in some physical situation, the problem can be considered as a two-dimensional problem. Therefore, the Module 3 of Chapter 5 is devoted to find the solution of a two-dimensional heat equation. In this module, we shall use the method of separation of variables to find the solution, and we shall find solution in different coordinate systems, namely Cartesian, plane polar and spherical coordinate system. First, we shall start with Cartesian coordinate system. So let us go to the first slide of this module. The heat equation in Cartesian coordinates is given by equation 1. So here we have considered only two independent variables, x and y. Now we shall apply the method of separation of variables. For that, we write the solution capital T as product of three functions, capital X, capital Y and tau, which are functions of small x, small y and small t respectively. Now if we substitute the value of capital T in 1, we get an equation which is written in equation number 2. First, we separate the time variable from x and y variable. For that purpose, the function of x and y are written in the left hand side of that equation and the function of t is written in the right hand side. Now let the separation constant is minus mu square. Here we have chosen the separation constant as a negative number because we want a bounded solution. So if we see the equation of tau, it becomes d tau dt equals to minus mu square kappa tau, and the solution can be written easily as tau equals to a1 e to the power minus kappa mu square t, which is a bounded solution, where a1 is the integrating constant. Now our aim is to separate the variables small x and small y. For that purpose, we separate in this way, which is written in the slide, and we again consider another separation variable as minus p square. So equating minus p square to the function of x 1 by x d2x dx square, we get the equation d2x dx square plus p square x equals to 0 and d2y dy square plus q square y equals to 0, where q square can be written in terms of mu square and p square as q square equals to mu square minus p square. And these two equations can be solved easily, and the solutions are written here. Capital X is a cos px plus b sin px, and capital Y is c1 cos ky plus d1 sin qy, where c1, d1, a, b are integrating constants. Therefore, the solution of two-dimensional heat equation in Cartesian coordinate can be written in the form which is given in equation number 3, where we have modified the constant in this way. Capital C is assumed as C1A1 and capital D as D1A1. Now we shall take one example where we can apply this type of solution. So, the example is presented here. The boundaries of the rectangle 0 less than equals to x less than equals to a and 0 less than equals to y less than equals to b are maintained at 0 temperature. And initially it is given that the temperature has the value small f x y. We have to find the temperature profile for t greater than 0. Now we are trying to find the solution of the above physical problem. So the temperature is given by the division equation which is written in the first equation. Now we have to solve this equation together with the supplied initial conditions and the boundary condition. The initial condition is given as capital T 0 y t equals to capital T a y t equals to 0 for 0 less than y less than b and t greater than 0, and capital T x 0 t equals to capital T x b t equals to 0 for 0 less than x less than a and for all t greater than 0. The boundary condition is given by, so these are the boundary conditions. The initial condition is given by capital T x y 0, that means at time t equals to 0, temperature takes the functional form small f x y, where f is a known function. Now the solution of two-dimensional heat equation can be written as we have obtained in the last discussion as capital T equals to a cos px plus b sin px into c cos qy plus d sin qy into e to the power minus kappa mu square t, where mu square equals to p square plus q square. Now if we apply the boundary condition t at x equals to 0, so in this equation we get, if we put x equals to 0, then we get a equals to 0. Similarly, t at y is equal to 0 gives, so if we put y is equal to 0 in this expression, that will give capital C equals to 0. Thus, the general solution reduces to this form: capital T x y t equals to b d sin px sin qy e to the power minus kappa mu square t. There are also two boundary conditions which are t at x equals to a equals to 0. So if we apply this condition in the above expression, we get sin pa equals to 0. So this gives p equals to m pi by a, where m is a positive integer. Now applying the boundary condition, capital T at y is equal to b is equal to 0 implies sin qb equals to 0. So this gives the values of q as q equals to n pi by b, where n is an integer. Now using the superposition principles, since heat equation is a linear partial differential equation, we can apply the principle of superposition to find the solution in the form capital T is equal to sum over m, sum over n, a mn sin m pi x by a sin n pi y by b e to the power minus kappa mu mn square t, where mu mn square equals to p square plus q square, which is equals to pi square into m square by a square plus n square by b square. Now in this solution, everything is known except the constant a mn, which depends on the values of am and n both. So to find the values of a mn, we need to apply the initial condition. the initial condition is given that the value of capital T at t equals to 0 is small f x y. So, if we apply this initial condition, we obtain a relation in the form small f x y equals to sum over m, sum over n, a m n sin m pi x by a sin n pi y by b. And from this expression, it is clear that this represents a double Fourier series. Particularly, this is a sine series. So, to obtain AMN, we can use the orthogonality property of sine series. So, using that, we can obtain the values of AMN as AMN equals to 2 by A into 2 by B into integration 0 to A 0 to B f sin m by x by A sin n pi y by b dx dy. Thus, the solution can be written as capital T is sum over m, sum over n, capital F mn sin m pi x by A sin n pi y by b e to the power minus kappa mu mn square t, where capital F mn is nothing but capital A mn, and the expression for capital A mn is given in the slide. Now, we are going to discuss the solution of heat equation in plane polar coordinate system. The equation in heat equation in polar coordinate system is given in equation number 4. Now, we shall use the same procedure, that means the method of separation of variables to find solution. For that, we again write capital T as product of three functions, capital R, capital theta and tau, where capital R, capital theta and tau are functions of small r, small theta and t respectively. Now, substituting capital T in equation number 4, we obtain an equation which is written in equation number 5. So, in this process, our aim is to first separate the variable small t. So, the function the expression which is function of t is written in the right hand side, and we assume the separation constant as a negative number as minus mu square. So, solution for tau can be obtained easily as tau t equals to e to the power minus kappa mu square into t. Now, it remains to separate the variable the function capital R and capital theta. So, in the next step or in equation 6, we have separated the function capital R and capital theta, and we assume the separation constant as lambda square. So, if we equate it with the theta equation and capital R equation, we obtain two equations which are written in this slide. And the theta equation is very easy to solve. The solution of theta equation is written here, C1 cos lambda theta plus C2 sin lambda theta. If you observe the capital R equation, this is famous Bessel's equation of order lambda. So, the solution can be written as capital R is equal to A j lambda mu r plus B y lambda mu r, where j and y are Bessel's functions of first kind and second kind respectively. Hence, the solution of equation 4, that means the original equation, is written in equation number 7, where capital A, capital B, C, D are constants. They are defined, the constants C and D are defined as C equals to C1e and capital D equals to C2e. Now we shall take one example where we can use the solution of heat equation in polar coordinates. So this is the example. We have to find the temperature in a long cylindrical region bounded by the surfaces r equals to a, theta equals to 0 and theta equals to pi. So in these three surfaces are maintained at 0 temperature and its initial temperature is given by the function small f. So for solution, we have to go back to the general solution, which is written in equation number 7, and we have to find the values of the constant A, B, C, D satisfying the given initial condition and boundary conditions. Now you note that in this equation, if we observe equation number 7, this equation is valid for all r. But in our present problem, this equation, this solution must valid for r equals to 0. But we know that the Bessel function of second kind is undefined at r equals to 0. Therefore, we have to take the value of constant b equals to 0. So from general equation, we can write the solution for our present problem as capital T is equal to j lambda mu r into c cos lambda theta plus d sin lambda theta into e to the power minus kappa mu square t. Now we have to use the boundary conditions. The boundary conditions are given that capital T is equal to 0 at theta equals to 0 and theta equals to pi. So this gives C, capital C is equal to 0 and t equals to 0 at theta equals to pi gives sine lambda pi equals to 0. So which implies that lambda must be an integer. So let lambda equals to n, and here we have taken only positive integral values. So n equals to 1, 2 dot dot. There is one more boundary condition, which is temperature equals to 0 at r equals to a. So this leads to the equation j lambda mu a equals to 0, and we have already found that the value of lambda is an integer. So this implies j n mu a equals to 0. Let mu 1 mu 2 dot dot be the roots of this equation. Thus the solution of for temperature can be written using the principle of superposition as capital T equals to sum over I, sum over n, a n I, j n mu I r sin n theta e to the power minus kappa mu I square into t. Now to find the values of a n I, we need to use the initial condition, which is written here, capital T r theta 0 equals to small f r theta. So if we use this initial condition, we obtain f r theta equals to sum over I, sum over n, a n I Jn mu I r sine n theta. Now to obtain ANI, we need to multiply both sides with r Jn mu j r into sine p theta, and then we need to integrate over 0 to a. This is the range for smaller, and 0 to pi, this is the range for theta. So if you do this using the orthogonality property of Bessel's function and orthogonality property of sine function, we can obtain the value of A like this: integration 0 to a, 0 to integration 0 to pi r f Jn sine n theta d theta equals to ANI times a square by 2 j n plus 1 square mu I a into pi by 2. Where we have used the orthogonality properties, the orthogonality property for Bessel function is written in the first equation, and in the second equation the orthogonality property of sine function is given. So in this way we can find the values of ANI. The expression for ANI is written in the last equation. Thus the solution or the required solution of the problem is capital T is 4 by pi a square sum over I sum over n BNI Jn mu I r by Jn plus 1 square mu I a into sine n theta e to the power minus kappa mu I square into t, where BNI is given by the equation which can be seen here. Now I am going to discuss the solution of heat equation in spherical polar coordinate system. The equation in spherical polar coordinate system is written in equation number 8. So now we are using the same procedure. That means we are writing the variable capital T as product of capital R, capital theta and tau, and we substitute T in equation 8 to obtain equation 9. If you observe equation 9, again we are separating the variable tau from R and theta, and here we are assuming the separating constant as minus mu square, because we want a bounded solution, and the solution for tau can be obtained easily as tau equals to e to the power minus kappa mu square t. Now the equation, our next aim to separate the variable capital R and capital theta. So for that purpose we separate that in equation number 10, and we assume the separation constant as k, and we take the value of k as n into n plus 1. Now the equation in capital R and capital theta are written in equation number 11 and equation number 12. So if you observe equation number 11, in this equation if you do the substitution, mu r capital R equals to mu r to the power minus half into s r. In terms of the variable capital S, the equation becomes d2s dr square plus 1 by r ds dr plus mu square minus n plus half whole square by r square into s. If you observe the R equation, this equation is not in standard form, so we give the transformation from capital R to capital S to obtain an equation in capital S, which is very known equation. So the solution of this is famous Bessel's equation, and the solution of this equation can be written as capital S as a j n plus half mu r plus b y n plus half mu r, where j and y are Bessel's functions of first kind and second kind respectively, and both the functions of order n plus half. So, capital R, if we come back to the variable capital R, we get the solution capital R as mu r to the power minus half into SR, which is written in the last equation of this slide. At equation number 12, this is not so much familiar to me, but if we give a transformation cos theta equals to mu dash, the equation 12 reduces to the form which is written in the first equation, and this is known to all of us. This equation is known as Legendre equation, and we all know that solution of Legendre equation is Legendre function. So, theta can be written as linear combinations of two Legendre functions of first kind and second kind. So, theta equals to a1 pn mu dash plus b1 qn mu dash, where pn, qn are Legendre functions of first and second kind respectively. So, if we substitute the values of capital R, capital theta and tau, and if we use the principle of superposition, we obtain the solution of the original equation as capital T equals to sum over n mu r to the power minus half into a n dash j n plus half mu r plus b n dash y n plus half mu r into c n dash p n cos theta plus d n dash q n cos theta into e to the power minus kappa mu square t. So, this is our required solution. Again, we shall take one example from spherical polar coordinates to make the concept more clear. So, in this example, we have to find the temperature distribution in a sphere of radius a, where its surface is kept at 0 temperature and its initial temperature is given by the function small f r theta. So, if we go back to the general solution, which is written in equation number 13. So, from this general solution, we shall try to find the solution which satisfies this particular boundary conditions and the initial condition. In the general solution, if you observe, there is the Bessel function of second kind which is unbounded at r equals to 0. Therefore, to get the bounded solution, we need to put the value of bn dash as 0. Again, if you see the Legendre functions, the Legendre function of second kind is undefined at theta equals to 0. So, to incorporate this fact, we have to take the value of dn dash equals to 0. Therefore, equation 13 reduces to the form capital T equals to sum over n, a n into mu r to the power minus half, j n plus half mu r p n cos theta into e to the power minus kappa mu square t. Now, we shall use the boundary condition. The boundary condition is given that the temperature is 0 on the surface of the sphere, that means T equals to 0 at r equals to a. So, this gives j n plus half mu a equals to 0. Let the solution of this equation is mu 1a, mu 2a and mu n a. Therefore, the solution can be written using the superposition principle as capital T equals to sum over n, sum over I, a ni, mu I r to the power minus half, j n plus half, mu I r, Pn cos theta, e to the power minus kappa mu I square into T. Now to find the values of the unknown constant a ni, we need to apply the initial condition which is given here. The temperature at time t equals to 0 is determined by the function small f, which is function of r and theta. So if we use this initial condition, we obtain the relation small f equals to, which is written here. And if you see this is a double series and this is mixture of Bessel series and Legendre series. So to obtain a ni, we first integrate it over minus 1 to plus 1 and then we integrate it over 0 to a dr. So first we first multiply the last equation with Pm cos theta and then integrate over minus 1 to plus 1 and the result is written here. But to obtain a ni, we need to eliminate j n plus half also. So to eliminate j n plus half, we again need to integrate this relation with j n plus half mu j r into r to the power 3 by 2 and then integrate over 0 to a. Now using the orthogonality property of Bessel function and Legendre function, we obtain the relation which is written in the first equation. And from this equation, we can easily get the values of a ni, which is written in the last equation. Hence, the required solution is capital T is sum over I, sum over n, 2n plus 1 by a square, b n I by j dash square mu I a into r to the power minus half, j n plus half mu I r, p n mu dust e to the power minus kappa mu I square into t. So here we have just substituted the values of a n I and we have defined the variable b n I in this way. The expression for b n I is written here and in this expression mu dash is cos theta. So this is our final or the required solution for the given problem. Thus in module 3 of chapter 5, we have discussed about the solution of a two-dimensional heat equation in different coordinate systems, namely Cartesian, plane polar and spherical coordinate system. We have used the method of separation of variables to find the solution. In Cartesian coordinate system, we obtain double Fourier system, we obtain mixed Bessel Fourier series, and in spherical polar coordinate system, we obtain mixed Bessel and Legendre series. In this way, we end this module.